Okay, we're going to continue the menu for today. We're going to continue our class exercise that will have two parts. One of them is this gas dehydration we're working with so far. And then we're going to look into how do we regenerate this TEG. Okay, we're not going to go into all the details how it is made, but basically how it is done. How does it work? And then if we have time, we're going to make an exercise in HYSYS. Okay, try to model a similar system but using HYSYS. Okay, so yesterday we were discussing the tower. We know that there are a few trays. Okay, that will be one from top to bottom, tray 2, and so forth. Okay, and then we found two lines. Okay, one of them is the equilibrium line. We said that the liquid leaving the tray and the gas leaving the tray, they are going to be in equilibrium. So they should fall on that line. And then we found an operation line that we made by making a mass balance between the top and any stage that is below. We can take 1 or we could take 2. Okay, we can make that balance with any tray. Okay, and then we said the following. We start, usually that's one way. Okay, people can start from bottom up also. So I have is the desired mole fraction of water in the vapor, in the gas. That's the water mole fraction in the TEG. Okay, remember, that's TEG coming down, that's gas coming up. Okay. And then we start our calculations. Okay, we know that Y1, okay, the gas coming out of the column, has to be in equilibrium with X1. That means that it has to fall on this line, on the equilibrium line. So here we'll find X1. Okay? Now we know that according to the operation line equation, that's the operation line equation. Okay? If we apply it for y equal to, that tells you that x1, y1. Okay, that tells you actually that this will be y2. Okay, that is the gas that is leaving the second tray. If you have now a third tray, okay, what do you have? Well, let's say we have only 2 trays, okay? What do we have here? Okay, so we can go to the right to find X2. Okay, and then finally we find Y3. Okay, Y3 will be the wet gas that I have from the separation, right? And X2 will be the wet TEG or the TEG with water to regeneration. Okay, and that's how I find exactly, how many, 1 stage, 2 stage, and I reach Y3. Okay, so now what happens? Okay, now I'm starting with Y1, which is what I want. Okay, but I actually can measure Y3. Okay, this wet gas, I can know the mole fraction. This is something I can measure. Okay, let's call it Y inlet. Okay, to the column is the mole fraction of water in the gas that is coming into the column. So what happens if for any reason this Y inlet is here? Okay, what does it mean? Well, that means that to achieve this Y1, right, with 2 stages, I should have a gas which has even higher water content than what I actually have. Okay, That means that when I use Y inlet, I'm going to achieve a fraction which is lower than what I need. Okay? Because that's really what I have. Okay? That's what comes from the separator. So if I reach here after 2 trays, if I reach higher than that, that means to achieve this purity that I desire, okay, this water mole fraction in the gas that I desire, that tells me that the inlet to the second tray is higher, okay, than what I actually have. That means that I managed to do it with 2 trays. Now, on the other hand, if I had the Y inlet was here, what does it mean? Okay, that means that even if I have 2 trays, okay, I still don't reach, because I'm going to start the process much earlier, okay? So I won't reach the quality that I need, okay? The mole fraction, water mole fraction that I need. So I need to add more stages. Okay, so let's put it here. And let's make a note. Okay, so if Y inlet is greater than Y3, this means not enough stages. Okay. If I do the calculation with stages, departing from what I need, actually I see, well, you know, I don't reach yet the inlet Y3. Increase stages. Okay. While on the other hand, if the Y inlet is less than Y3, that means that there are more than enough stages. Actually, I could use maybe 1.5, okay? The thing is that the stage is an integer thing. I cannot decide to put half, 1/3, I have to use 1, okay? More than enough. Okay? What is the effect of increasing L? Okay? If you remember, L was, let me move this below. Okay? What is the effect? What happens when we increase L? Okay? Okay? L is basically the slope, okay, of my curve, of my operational line. So I have 1, let's make the base case, which was like that, okay, L over G, that's the slope, and then I have my equilibrium line. And what happens if now L increases, okay? That basically tells you that if I put the same number, I'm going to get a higher value of Y, right? So that means that my equilibrium, my operational line will be something like that. Okay, for example, for L prime bigger than L. What does it happen with the number of stages? Okay, if we start from the same point, right? But now we go up much higher, you see? While in this case, I will have to go to here. Okay. Then I reach this point, and maybe I go higher. Okay, so that means I achieve much faster. I achieve Y inlet. Y inlet, let's say, is someplace here. By changing the inclination, which is, you know, kind of logical. When I increase the amount of TEG that is flowing through the column, I should be able to make it in less trays. Okay, it should require less trays to make it. If I use less, then the line becomes flatter, and then I need a lot of trays to reach this Y inlet. Okay? So our task was, we got a problem, okay, that we were started to solve yesterday, and I think we outlined a procedure, okay? Determine the water content in the inlet gas stream. That we have done with the equation, with a BBA function that represents the plot. We said this gas has 1 ton of water per million standard cubic meter. Okay? Then we find the desired. The desired says that this gas coming out should be at the dew point when I reduce the temperature all the way to -10. Okay? That means it should be dry gas, all the way -5, -6. But when I reach -10, I should have condensation. Okay? So for that, I go again to the diagram with -10 and 68 and see how much water is, because it will be saturated with water at that pressure and temperature. And I find that is 61.8. Okay? That means that the difference between these two, okay, which is 939, okay, or 38, that is how much I have to take with the contactor, with the TEG column. Okay? And that's the next calculation we have made. We have to remove 2 tons of water per day from that gas in the contactor. Okay? And that's what we have done so far. Now, the next thing is to know the number of trays. We have to build the 2 lines, okay, that we were discussing. We have to build the operation line and we have to build the equilibrium line. So for the operation line, we said we have this equation, okay, y I plus 1 L G. G we have, that's the molar flow rate of gas. Okay, times xi minus x0. This we have, that's the purity, the water content in the TEG that is entering, okay, plus y1. What is y1? Is the desired, and this we also have, right, the desired molar fraction of water in gas. Okay, so we have almost everything we need. Okay, the only thing we need is actually to convert. Okay, we have the molar rate at standard, the rate at standard conditions. Okay, we know that is how much is it? 2.8 million. Okay, so that's, let's call it, let's continue with the steps. Okay, we have step number 4. Okay, 4.A. And 4.A is basically estimate, calculate G. So how do we change from this rate to molar rate? Okay, so how do we change the units from standard cubic meter per day to molar rate, to kilomole per day? Okay, we use the equation of state. Okay, remember we have PV volume nRT set. Okay, set nRT. We have to apply that equation for standard conditions. Okay, that's where I'm measuring this rate, is in standard conditions. For standard conditions, okay, P standard condition is 1.01325 bar. T standard condition is 15.56 Celsius. Z is 1 because it behaves like ideal gas. Okay, and what do I want to clear from here? I want to clear actually the volume divided by N. Okay, or actually the opposite. That's what I want, because that's the, I need the molar density, which is N divided by V. Okay, let's call it rho with a bar on top. That's what I need, right? That's what is going to change. The units are kilomole divided by standard cubic meter. If I multiply that density by the rate, then I find kilomole, okay, per day. So N divided by B is how much? Is P standard conditions, C standard conditions, R universal gas constant, and T standard conditions. Okay, so how much is that? The molar density is, I think I had it here someplace. molar density, okay, P standard conditions divided by R, T standard conditions multiplied by 1, okay? It's 0.042 kilomole per every standard cubic meter, okay? That shouldn't be, you know, that we should have done that in class, but I guess I forgot to erase it, so tough luck. Okay? And then when we multiply, so we have to multiply the molar rate of gas will be Q of gas times the molar density of gas. So that is 2.83 times 0.042. Okay, and then I end up with, so that will be G. Okay, G will be this number, the molar density multiplied by the rate, and be careful, this is in millions, so I should multiply 1e to the 6. Okay, and I get 120,000 kilomole per day. Okay, so let's see. Now on the equation we have G, that was solved, right? We have X, that we have it as an input, someone measured for us. And then we need, then we need this guy, okay? The molar fraction of water in the gas. So let's make question will be 4.B. Okay, we need Y1, and Y1 is the number of moles of H2O, okay, at the inlet divided by the number of moles of H2O at the inlet plus the number of moles of gas at the inlet, right? We are now talking about the stream coming into the column, okay? This stream here. Sorry, the stream coming out of the column. So it's out. No, it's not in. That's out. Sorry for that. Okay, so it's out, out, and out. How much water do we have out at the outlet, in the gas outlet? We know that, right? We know that RSW at the outlet is how much? That's the one that I want, right? Was 61.8 kilogram per million standard cubic meter. How many moles of gas we say is the same? Okay, we say it remains the same. Therefore, we can say that the Q of water at the outlet will be equal to RSW at the outlet times Q of the gas, right? That's how much water we have. So that will be 283 times RSW, so that will be 61, I guess, 61.8. Yeah. So how much is that? 2.83 times 61. Okay, 174.89 kilogram per day. okay? But I need not the rate, okay? I need the moles, okay? The number of moles, the molar rate. So how do I convert from mass rate to molar rate? Simply dividing by the molecular weight, right? So I just say, and this should be not Q, okay, but it should be M, basically, because it's a mass flow. Okay, so the number of moles of water at the outlet will be simply the mass flow of water at the outlet divided by the molecular weight of water. Okay, and that will be 174.89 kilogram per day divided by the molecular weight, which is 18 kilogram per kilomole. Okay, and I divide and I obtain the units that I'm supposed to get, I hope. Okay, then this number divided by this number, okay, kilomole per day. Yeah, let me here just add one more column, okay, so we can, one more row. Here we can see mass water outlet. Okay, that will be kilogram per day, and that is simply these two, this guy times this guy, and then we have the N of water, and that will be in kilomole per day, and that will be simply this guy divided by this guy. Okay, 9.72. Kilomole. Okay, how do I find now the fraction of water at the exit? Okay, how do I find Y1? Y1 is simply the number of moles of water, okay, at the outlet divided by the number of moles of water at the outlet plus the number of moles of gas at the outlet. Yes? So simply I come and divide, where is it? Y1 will be this number of moles divided by the number of moles of gas plus the number of moles of water. And it should be a very small number. That's how much water it has. A mole fraction of 8 to the minus 5. Very small. Okay? Even though you feel like a big number, okay, it's 61 kilogram, but it's per million. So it's very diluted. If you take the whole gas, it's a very small concentration. And that can still give you trouble, okay, this fraction. So now we found Y1, okay, so which was 8.11 e to the 5. That's a fraction, okay, that doesn't have any units. What is the next step? Let's look at the equation. What do we need to find the equilibrium line? Now we have this guy, we have this guy, we have this is what we are going to change, right? And we need L, okay, which is the amount of TEG that I'm injecting. And if you remember from last class, this equation, or the balance, okay, when we made the balance in the whole column, the mass balance, where is it? The mass balance, okay, I told you that I can be two ways, okay? I give the rate of TEG, but then I find the X, how much water has the TEG leaving the column, okay? Or that I can give you that, the amount of water that is in the TEG leaving the column, and calculate L, okay? So let's do it the first way. Simply I give the rate, okay, of TEG. So that will be question 4.4.C. Okay, so calculate L. Okay, and for L we are going to use a rule of thumb, okay, that people with experience, they have said, well, this, I know that I need something between 12 and 40 liters per kilogram of water, of TEG per kilogram of water. Okay, experience. Simply people try. If you say, if you use too much, then you're just wasting. It's not very efficient. Okay, you're having too much liquid. But if you use too little, you have too little mixing. So you need a lot of trace. So the optimum lies someplace in between. Okay, we're going to use the value recommended for this gauge, which is 33. That's what I need. Okay, 33. We're going to use, we will use 33 liters of TEG per kilogram of water. Okay, so how many, do you remember how many kilograms of water we have to remove? That was someplace here, right? Mass flow of water to remove. 2670. Okay, the mass flow of water to remove is 2670 kilogram per day, and I know to remove that water I need at least, the TEG will be 2670 kilogram per day times 33 liters per kilogram. So how much is that? Let's calculate 2670 times 33. That gives me 88,110 liters per day that I need to inject of TEG, okay, in the column. But really, remember, they have to be in the same units, okay, L and G. When I put them both in the equation, they have to be able to cancel each other, okay, so they have to be in the same units. So I have now to take that to number of moles of TEG, okay. So how do I do that? And that actually will be not M, but will be a Q, okay, a rate of TEG. The mass flow of TEG is simply the Q of TEG multiplied times the density of the TEG. Is a liquid. It will be a bit affected by pressure and temperature, but not very much, okay? So we're going to use a constant density that is given here, 1130, 88,110 liters, divide by 1,000 to bring it to cubic meter, and then I multiply 1130, which is kilogram per cubic meter. Okay, therefore they cancel. This cancels with this one and this with this one. Okay, how much do I get here? 88,000 divided by 1,000 and multiplied times the density. Okay. Okay, 99,000. Let me see if I did it correct. B10, 11, I think so. 564 kilogram per day Okay, this is per day. This is liters per day. Okay. Now finally, how do I get molar flow? Divide by the molecular weight, right? So N of TEG that I have to inject, which is equal to L, that will be M of TEG divided by the molecular weight, and that will be 99,564 divided by 150. Okay. So I copy all of that, and I'm going to put it here in L. Divided by the molecular weight. $150. Okay, and you see the amount 664 kilomole per day. Okay. How much that is that compared with the water that I have to remove? Okay, we made an assumption, if you remember, that L, the assumption was that L is constant in the column. Okay, if you remember the amount of water to remove, how much was it? 2,670 kilogram per day, right? And how much is in number of moles? Is that number divided by 18, right? So how much is that? 2,670 divided by 18. Okay, 148 kilomole per day. And here we are obtaining 664. So it's not a very good assumption, okay? 664 kilomole per day. Okay, it's like, how much is that? It's like maybe 20%, something like that. Okay? But we are making that assumption, so, but just be aware that it's not really a good assumption. Okay, next step. What do we have? We have L, we have G, we have XO, we have Y1. We have everything we need, right? So we can start making the line for the column. Okay, the line, the operational line. Okay, what is the, yeah, let's do it, maybe we do that first, the line. But before we do it, we have to plot it, right? So now we have everything we need. We have L, G, everything. And we're going to start making our plot. Okay? We know we want to start in x0, which is 0.1. And we want to start on y that was 1, okay, which is 8 e to the 5. Okay? These 2 points. And then I'm going to continue with that line. Until which value should I continue? Until which value should I plot that line? Remember, we are looking for Y inlet, right? Y inlet is the amount of content of water in the inlet gas. Okay? And we want to make our line almost all the way up to there. Okay? So first I will say, before plotting, we should find out, where is our Y inlet, or what is our Y inlet. So how do I calculate that? That is this yn plus 1. That will be our step 4.d. Okay? We want to calculate Y inlet. Okay, and Y inlet is yn plus 1. Okay, depending on the number of trays you have. I calculate exactly the same way, right? We have the RSW at the inlet, which was 1,005 kilogram per million. Okay, then we can calculate the mass flow of water at the inlet, which was this 1005 times 2.83. Then I can take the number of moles, right, of H2O at the inlet. It will be mH2O at the inlet divided by the molecular weight of water. Okay. And finally, I find the Y at the inlet, which is number of moles of H2O at the inlet divided by the number of moles of H2O at the inlet plus the number of moles of gas at the inlet. Okay? Exactly the same way we have done now at the exit, we are doing it at the inlet. Okay, just to find out how far do we have to draw the line, how far it has to go up. Okay, so we say, do we do it in one go? We can try. Okay, this number times the flow of gas, okay, this number here, and then I divide by molecular weight of water. Okay, that gives me the number of moles of water at the inlet, and then I have to divide that by the same quantity plus the amount of gas entering into the column, and that will be this amount of gas here. Okay? I think so. Okay, and it tells me that the gas that is coming in also doesn't have a very high mole fraction, water mole fraction. If you see, it has simply 1 to the minus 3. So that gas has 0.999 or 8 other than water. Okay, so really the amounts that we are handling here, they are very incredibly small. Okay, so that gives me 0.00132. So we want to go from 0, we want to go from Y inlet, which is 0.00132. We want to go to Y1, which is the Y at the outlet, which is 0.0000811. Sounds crazy, right? It's just such a small quantity. But that quantity can cause a lot of issues, can cause that you will be fired, you know, if though you don't care about these 2 zeros, okay, extras in the. Okay, so now we know until which value we have to make our plot. Okay, we have to start. If we go here back to our plot, has to be from 8 to the 5, and here it should be made at least at 0.001. At least. Okay. What will be, let's make another step, okay, even before making the line. Let's make 4.E, okay, which is to how, what is xn, okay, which is the amount of the molar fraction of water in the TEG exiting the column. Okay, we just want to know with the conditions that I have, okay, what is the amount of water that is in the TEG exiting the column. Okay, we know what is coming in. The TEG has 10%, where is it? 10% water. And then we want to know, we know it will be bigger than 10%, but we want to know how much. For that we go to the equation of the whole column, okay, that is this equation. And we clear from here, we have everything. We have G, we have Y, we have Y1, everything. We just have to clear from that equation xn. Okay? So we said G times what coming in, it's coming out y1 plus L times xo0 will be equal to coming out xn plus g times, no, sorry, is the opposite, should be here. This is what is leaving the column, and this is what is entering the column, g times y n plus 1. Okay? This is entering from the bottom. No, this is leaving from the top. This is leaving from the bottom. Liquid and gas leaving from top and bottom. This is entering from the bottom, and this is entering from the top. Okay, so the gas that is coming in should be equal to the gas that is coming out. And then we clear from here, clearing xn. That's the only thing we don't have. Okay, we have already estimated this guy, this guy, this guy, this guy we estimate, this guy we have, all of them. So I can clear xn. And xn will be yn plus 1 times g plus L x0 minus g y1 divided by L, and that gives you, so let's use that equation in Excel, and for that I might need your help. That will be y gas entering times the mole fraction of gas plus the liquid entering, which is from the top, times the mole fraction of water, okay, minus leaving, the gas leaving from the top, which is G, times the water fraction of that water, which is Y1. And all of that divided by L, which is this guy here. 30% molar fraction. That means the TEG entering the column from the top has 10% of water, and then when it's leaving, it has 30%, 32%. Okay? So now we know already the bounds, okay? We want to make that plot for until y inlet, and we want to make it all the way to 30%, okay? 33%, 32%. So we now know the range of our column, of our operation. So let's make that plot, and then we take a break, okay? Because I think all of us need a break. We're going to start with x0, which was that number here, 1. And how should we make the steps? Let's see every 0.5, okay? You can choose any step you want. But let's say the previous plus 5 e to the minus 2. Okay? So you will have in steps of, and you have to drag it all the way to 3. Let's make it until 4, okay? 1, 2, my column will be up to here, 3.5, okay? But let's make it all the way until 4. And why? For that we have to use the equation of the column, okay? Which is this equation here. But I have programmed that for you already. So simply you have to go Alt F11. And you have TEG operation line, that's the equation we need to use. So that will be TEG operation line, taking L, and I have to freeze it, G, freeze it, X0, this first point, freeze it, Y1 is here, also freeze it, and X. Okay? And now we see how it looks like. That's the equation. Okay, that's how it looks like. Okay, we have the two equations and the other equation. So that was, let me just write here, that was 0.323. Okay. And that's what we find, okay? That's the operation line and that's the equilibrium line, okay? And the equilibrium line I just have made with K, okay? And you have to give some values of X in the range, okay, that you want. Okay, I should have put here all the way until 4. But then you simplify Y by multiplying X times K, okay? And that gives you the two lines. So let's see here the results and let's see how many stages we need before we go and take a break. Okay? That will be this point here in the operational line is x0, okay, and y1, the desired, okay? I want to have 8 to the minus 5, okay? So that 8 to the minus 5 is here. What is the first step? I calculate the liquid. This y1, if you remember, let's make the plot. We have the tray number 1, and here we have y1, we have x0, and we have y2 and x1. Okay? Therefore, x1 and y1 are in equilibrium. So with that, I find x1. Okay? There I have one tray. Now I know y1 to find x to find the y2. I go back to the operational line. Okay, now go up. Okay. Where do they have the y of the inlet? Okay, what I have at the inlet. The y at the inlet is 132. Okay, so let's make it here 132. That's y at the inlet. Okay. Now I go to the right, the second tray. Okay. Here I find x2. Okay. Here I find. Here comes x2, and here comes up y3. Okay. Where do I find y3? This will be y2. Where is y3? All the way up. Okay, it will be someplace here, very high. Okay, that means it's enough with two trays. Okay, because here the y I find, the y at 3 is bigger than y inlet. That means only two trays are needed. Okay, it's not easy peasy. Okay, it took a lot of time, but you have to understand always. I think it's good when you make that all the stages, you look at that diagram, okay, and see where you are, which one is 2, which one is 1. It can get confusing, okay, this direction, but that's the way you find how many trays you need. Here you have one tray, and here you have two trays, and that's it. You don't need anything else. Okay, at least for that break. Should we take one more thing before the break? What happens if we increase L? Okay, now we don't use 33. Okay, but let's use, let's say, less. Okay, let's say we use now 10. Okay, changed. Yeah, so let's say here, what happens if L is reduced? Okay, that means I'm going to use 10 liters of TEG per kilogram of water. Okay, and let's see how that affects my calculation. Okay, so I have this. That will be the homework. Okay, so I don't want to spoil all the fun for you, but I just want to take a quick Okay, if we made everything consistent, we didn't screw anything up on the Excel sheet, which I hope is correct. Okay, so we have the first stage, or the tray Y1XO, then we come here, then we have Y2, and here we have, that will be X1, X2, Y3, X3, then we go on this line, let's continue up, okay, it's not so straight now. Okay, where is the Y inlet that we need? It's around here, okay, that's the Y inlet. Okay, so we need to 1.2. Okay, then I go up, Y4, X4, until finally I reach higher. Okay, that means I need, compared to that case, if I use 10 liters of TEG per kilogram of water, I need 4 stages. Okay, I need to make the column, and that means making it longer, taller. Takes more space, weighs more, transportation is heavier, so we prefer to add more TEG. Okay, but here I need 4 trays are needed. Okay, let's take a break and then we come back with the regeneration part. Okay, but let's take a break, let's say 15 minutes. So come back here, 25. Okay, let's go very quickly into the regeneration of the TEG. Okay, in the TEG, we basically have in the stream, if we see, that is, that regeneration means basically removing the water from the TEG, okay? From the wet TEG leaving the TEG column. Okay, the dehydration column. This TEG will have some water. We said we cannot simply dump it, even though TEG it's a green chemical. So in principle, could just dump it to the sea, okay? Because it's not harmful to the environment, but it costs a lot of money. Okay, so we want to regenerate. The way we do it, okay? Add exit. So let's say add column exit. Remember, we had around 69 bar for our example and 38 degrees Celsius. And on those conditions, everything is going to be mainly, let's put the TEG. Okay, we have here our TEG, and here we have our water, okay? And everything will be in the liquid phase, okay? Everything will be like a liquid. The main strategy is to simply to warm up, okay? To heat that up. So we have 2 processes. So now go at regenerator. Okay, what we make is that we drop the pressure at 1.01325 bar, okay, atmospheric pressure, 1 bar. But then the temperature, we increase it very high to 200, approximately 180, 200 degrees Celsius. Okay? And what that's going to make now is that actually I'm going to have 2 phases. Okay, I'm not going to have liquid anymore, but I'm going to have 2 phases. I'm going to have a clear interface. Okay, let's make it with another color maybe. So we're going to have, that will be liquid. Okay, and this phase will be gas. And in the gas, actually we're going to have a lot of water. Okay, the main phase that is going to vaporize will be the water. Okay, and of course some TEG will be also vaporized, but not very much. Okay. While on the liquid part, we're going to have everything is going to be mainly TEG. Okay, mainly TEG. And then we're going to have still some liquid water that doesn't vaporize. Okay, so that will be water. What we have here is water, H2O. And what we have here is TEG. Okay, when we boil it, we lower the pressure and we boil it, most of the water becomes vapor, and then I can simply drain it. Okay, if they are in different phases, it's very simple to drain. I just have a separator. Let me see if I have an image someplace how. Maybe here. Okay, I simply separate, take from here, I take out the gas, okay? The vapor. Let me just copy that so you have it. You don't have to, I'm not going to go through the details how the process is done because essentially you have to, you drop pressure with a valve, okay? And then you have to heat it, okay? So you do that in different steps. You do that step, one is heater, a preheater. Then you have another heater to take it to 204, and finally reach this vessel, okay, where you have the regeneration. Okay. Then you have the TEG, which is lean, okay. You drain the TEG out from this lower part, okay. This TEG, this liquid coming here, which is lean. That you should make it now, take it down to 38, okay. That is at 200 degrees Celsius, so you have to take it down to 38. So sometimes you use that hot stream to heat this cold stream, okay, and you use this cold stream to cool the hot stream. So you have all kind of strange processes that are crossing each other, but it's simply to use the heat that I have to leave from some stream to warm some other stream that is going the other direction. Okay, but we are not going to go too much on details into that. Okay, we're just going to go into how the process is done. Okay, so here at this regenerator, I simply can take mechanically, okay, separate the liquid from the gas. Okay, from the vapor. Okay, and in the vapor is mostly water vapor, and in the liquid basically you have mostly TEG, okay, because simply that's the way they split. So that's what we are going to do next, okay. Simply we're going now to calculate, how do we calculate equilibrium of a mixture? You remember? We use something called Rutherford-Rice, right? That we saw that in week number 2. Okay, to calculate how do these phases split, we use Rutherford-Rice. Okay, so let's use Rutherford-Rice to calculate the splitting. Okay, and the splitting means the Y, so that means at a temperature of 200 degrees Celsius and a pressure of 1.01325 bar, calculate YH2O, XH2O, YTEG, and XTEG. Okay, the mole fraction of water in the vapor, mole fraction of water in the liquid, mole fraction of TEG in the vapor, mole fraction of water of TEG in the liquid. Okay? We are going to use Rutherford-Rice again, that you are very familiar with and you should have no problem doing, right? You remember very well from. And that's this part, okay, that regeneration. Here we have, actually it's not 200, 199, okay, and a pressure of 1 bar. So the first step, if you remember, for Rutherford-Rice was to estimate this K, this splitting factor, okay? That K, so that's the first step. Let's copy that exercise here. That's a regeneration part. Okay, we need the K, okay, the K values which are a function of pressure and temperature. We can use an approximation that we didn't discuss at that time in separation because it sometimes doesn't work very well for hydrocarbon, okay? But we can say using Raoult's law, okay? Raoult's law, I don't know if you saw it someplace, but basically tells you that the pressure times Xi of that component will be the vapor pressure times Yi. That's the partial pressure, what is called the partial pressure. Okay? And that's Raoult's law. Okay, should be with an apostrophe here. Okay, I think he was French, I think. And that tells you that basically Yi divided by Xi should be, and I think it's the opposite, okay? Sorry for that. P, and this is PV. PV over P, which is exactly equal to the K factor, okay? Yi divided by Xi, that's the K factor. So if I have the vapor pressure and I have the pressure, I have K. And the vapor pressure is simply where do I have boiling, okay? Where do you have the change of phase? Okay, boiling pressure, if you remember, for a pure substance, let's make it bigger. I don't know why. I'm not getting charged by the space, so I don't know why I make it so small. At least they're not charging yet, okay? Maybe they will charge in the future, but not now. Okay. We have P and T, or sorry, T and P. Okay, and we have one line which is a saturation line, right? So we said for water at 100 degrees we have 1 bar, okay? There we have a change of phase. So that's what we call the vapor pressure line. Okay? So we just have to find a way for each pure component simply to calculate that value, and then we divide by the pressure, and that's our K. Okay? There was another French physicist, chemist, that he found called Antoine. Okay? That he found an expression of PV has a function of temperature. Okay? And they have been using the same expression, they have been recording these expressions for different components. Okay? And the way the equation looks like, you have it on your Excel sheet. Okay, where is it? PV Antoine. Okay, the expression looks like that. And I need just some constants. Okay, they did some measurements in the lab. So for each substance, they need A, B, simply constants, okay, a correlation you measure in the lab. And that's what we are going to use here, okay? We have a correlation with A, B, and C for water. A, B, and C are constants for each pure substance. And it's a function of temperature. So with that, we calculate the vapor pressure. With vapor pressure, we divide by pressure, and we find the K. And with the K, we're happy. We can run Rutherford Rice, just like what we have done before. Okay? So let's do that for our exercise. PV is PV Antoine. Okay? That requires the temperature. We have to check the units. I think it's in Kelvin. A, here I'm calculating for water. A, B, and C. Then I drag it down. So that means water to vaporize at that temperature, it needs, how much is that? 16, I have to find the units, kilopascals. Okay? 1,000 at 200. Okay, temperature is in Kelvin. Okay. Now the K factor will be the vapor pressure divided by the pressure that I have, and the pressure I have to block it. Okay, 16 and then 0.73. Remember then what I did? I had this function which was the Rashford-Rice. Let's go back to our class, one of the first weeks, right? That's where we have seen it. Okay, it was here. You thought you were not going to see that anymore, but you are going to see it. Okay? Remember the Rashford-Rice function was this guy here. I give K, I give Z, and then I iterate with FB until it's equal to 0. Okay? So that's what we have to make. So we have the Rashford-Rice term. For that we have the equation, okay, which is a function of Z, is a function of K, and is a function of FB. That is the same for all of them. Okay? And what number should we try first? Let's try 0.3. Okay? And the sum of these two. That is what I have to drive to 0. Okay? Also one thing, what composition do we have to use here? That is a composition of the TEG leaving the column, right? So that actually what I have to use here, this set, this should be the composition of the TEG, composition of the stream, composition of the liquid stream leaving the column. Okay? That means that here I need xn. Okay? That's what I need. Okay, and how much was that for our exercise? If you remember, we have made the calculation someplace here. 32%, okay, was something like that. Sorry, it's not this one. Oh, yeah, because we changed this number, right? Should be 33. 0.323. Okay, so that will be the Z of the water, 0.323, and the Z of the TEG will be 1 minus that. Yeah. So that's what we want to regenerate. That's what we want to. Okay. Now the next step. Let's see if it works. Okay. Always with Rashford-Rice there are some surprises. We want to change this guy. We want to take it to a value of 0, right? By changing this guy. And subject to the constraints that that number, B5, should be less than 1, and that number should be greater than 0. Okay, it found a solution, 0.3, actually was very close, for some reason, okay, our assumption. Xi, how do I calculate? We have to go back to our class at that point, but Xi basically, we can use this expression, okay, and I have that program for you already. As you know from the first exercise, you have now to make memory to FB, I block it, and KI. Okay. Now you see that is the liquid, okay? That is the resulting composition of the liquid. You see that liquid has 94% mole fraction of TEG and only 5% mole fraction of water. Okay, that's really what we want, that it will be very rich in TEG and has a little bit of water. And Y will be simply this value times the K. Now this is very, you see, you're stealing part of the TEG. Okay, part of the TEG is going out with the water. okay? But it will be purely water. Okay, so let me copy that. Okay, those are the results that we have. Okay, and this is the composition of the liquid. Okay, liquid that I'm going to take back to the absorber, back to the tower, put it from the top, and this is the one water vapor that I'm going simply to take out. Okay, I'm just simply going to release to the atmosphere. Okay, now let's say how much TEG I'm losing in this process to see how much I have to make up. How do I calculate that? Okay, how much TEG I'm losing? The question is how much TEG am I losing to the atmosphere? Okay, how do I calculate that? Well, first I have to calculate, right? I have N vapor, which will be the N, total N. I have an N coming in, then I have two N's, okay? N going to the vapor and N going to the liquid. Okay? So I want to calculate first N of the vapor. Okay? That will be N times the FV, okay? That's the vapor fraction. And then after that, to calculate N of the vapor TEG, I simply have to multiply N times FV times Y TEG, okay? And that I will see how much I'm losing. Okay, what is the N that is coming inside this process? Is simply L, right, plus the amount of water that I'm removing, okay, times, let's call it W, okay? So that will be from our last exercise is how much? L was 664 kilomole per day. And how much was the water that I'm extracting? I think we did that here. The water that I'm extracting is this number, okay? 148. Okay, how much is that in total? The number of moles I'm producing with my column. It's okay, 812. Okay. Now to calculate N vapor, that is 812 times 0.33. Okay, how much is that? 303, sorry. Okay. See how much is that? This times 303. Okay, 246. 200, right? And 46. And then how much of that is TEG? N vapor going to TEG is 246 times the Y of the TEG, which is 0.0581, and that's how much? 14 kilomole per day. That means that I'm losing, okay? Instead of having 664, I'm losing now 14 to the environment. How much is that in let's say kilogram, for example, that I'm losing. 14, the mass fraction of vapor in the TEG. That's 14 kilomole per day times 18, right? 150 kilogram per kilomole. How much is that? 2,141 kilogram per day. I'm losing 2 tons of TEG, simply are evaporating. Okay. I hope we did the calculation correct. Okay. But it looks correct. Okay. So I'm losing 2 tons of TEG every day, so I have to replenish that. I have to have some makeup of TEG. Okay. So it's very simple. Simply evaporating. I take the liquid that I have. Very simple. I take it to high pressure, high temperature, low pressure. That causes all the water to vaporize, and then I can find exactly what is the purity. Okay. And actually, I shouldn't have used the purity of. Remember here we use 0.1. Okay. But actually, the purity after regeneration is much lower. Actually, 0.6. Okay, so we should have used that purity of the TEG. Okay, we are now close to the end of the lecture, so I'm wondering if we should try to make very quickly a HYSYS exercise, or if you're okay without knowing how to do it in HYSYS. Should we try to make it very quickly? Yeah. Okay. So let's go to farm. Let's see, hope that everything works as it should, okay? It's really simple if everything works. Okay. Let's make it first. We could use the full composition of the gas, okay? But let's assume it's purely methane, just to make our life simple. Okay, so I'm going to add methane. I'm going to add TEG, okay? Triethylene glycol is here. And I'm going to add water. Just these 3 components. In reality, I should use the full composition of the gas. Okay? Now I go to the fluid package. Those are the only 3 I'm going to use. Fluid package, we could use an equation of state like Penck-Robinson but there is one option here that is called glycol package. Okay? Which is simply a cubic equation of state, but it's a bit customized for glycol calculations. Okay? Remember I told you they changed beeps, they changed some things, so this is an equation customized for that. Okay? After that we go to simulation, and to make the column we need a few things, right? We need the stream coming in, okay? We need the stream of gas coming out, we need the stream of TEG coming in, and we need the stream of TEG coming out. Okay? We need these 3 before we put any column. That will be the gas coming in, that we have, what is the temperature? 38. The pressure was 69 bar. The molar flow, we had it, right? Was G, and that G is 120,000. Let's put it in hours, because I think those are the units HYSYS needs. 24, 499, 4990. Okay, so let's put that here, 4990, and we need the composition of that gas. And what is the composition? There is no TEG in that gas. How much water does it have? That will be yn plus 1, right? 0.00132, 0.00132, okay, and the methane is the rest, okay, which is 0.999, no, sorry, 87, you see? Okay, it gives you one. Okay, now I have everything I need on the inlet, okay? The other thing we need is the TEG inlet, okay? We need this TEG. There we had, again, 38, okay? Then we had the pressure was 69 bar, because we are using a pump to reach to that pressure. Molar flow, that will be L, okay? And L was 664, let's change that to hours, okay, divided by 24, 27.7, 27.7, and the composition of that stream, no methane, okay, has TEG. It has TEG. How much TEG it has? 90%, okay, but it has 10% of water. Okay, and we have everything we need: pressure, temperature, and rate. Now these two are going to be calculated by the column. How do I put the column? Let's see if let's say first, in case it crashes. I'm a bit afraid. Every time working with columns, you have to be careful. Absorber column is this column, okay? You see from the picture, it has 2 inlets and 2 outlets. So I connect, okay? What is the inlet? Bottom stage inlet. That's the gas, wet gas. Okay. The glycol coming in, where is it? Top stage inlet, okay? That's number, is it 3? 3. Okay, we should move it to the right. Now, outlet, that's the dry gas, okay, so that will be 2. Okay, and then I need the bottom, that will be the rich TEG, okay, that will be 4. Here it's using 10 stages, let's leave it for now. Next. Top stage pressure, we say, is isobaric. Mostly, remember, we have some hydrostatic difference, okay, due to the column. But let's say it's the same, okay. Let's say 69 isobaric. Then you will have the K will be slightly different. 69 bar, okay, and then next, okay, and then done. Before doing anything else, I just want to make it nicer. Let's put 3, that's the MEG, and we can even change the name of that stream. So that will be wet gas. Okay, that will be TEG, that will be lean TEG. Okay, then we have number 2, that will be what? The dry gas. Doesn't want to make dry gas. Okay, and finally we have this number 4, which is the wet TEG. Okay, to run it, I say once more, I enter into the column and then I click run. Okay, it converged with 10 stages and it tells me now that, let's see the fraction that we get. Okay, close to 30%, 26, what we got just now. And then the dry gas should be very low content of okay, 0. Actually, we cannot see the number, we have to paste it in Excel. Okay, 8.77. Okay, similar to the numbers we just found here. Remember, we were doing an approximation, assuming that the rate is the same, the molar flow is the same, so the results shouldn't be exactly the same. But you find from here that at least, it looks like a good approximation. And you can change the number of stages to see how that affects your result. Okay, you can change, for example, to 4. Okay, and then you run, it converge, and then see how it changed your result. Okay, easy peasy. Okay, so just now to close, do we have any questions that you're burning with a question that you want to ask that you didn't understand? No? Okay. So next class, according to our plan, you are going to in the hands of Harald. Okay, he's going to teach you. And you're going to go through most of the fundamentals on flowing pipes, okay, heat transfer, heat exchanger, and compression. Okay. So thank you very much, and have a nice week.